have the pleasure of taking electrochemistry to new heights. And by new heights, I mean exploring its calculational dimensions that have not been done previously on YouTube to that extent. Electrochemistry is not just electric potential or redox potential or left hand side minus right hand side. It's a lot more than that. It's about the electrons and cations traveling to their respective electrodes, cathodes and anodes respectively, across the electrodes, set up and supported by a circuit. And without these components, an electrolytic cell will not be able to function. So that's the ammeter, that's the resistor cross, which is a voltmeter, that's a switch, that's a battery. And we have to realize that the laws of electricity apply to electrolytic cells as well. So in a parallel circuit where the resistors are in parallel and in a parallel circuit where the electrodes are in parallel one hand, the current would stay constant. The current would split, but the voltage would remain constant. And in a series circuit, current would remain constant and the voltage would break. So these laws will apply to electrolytic cells because they're dictated by electrolytic ohmic relationships, because these metals obey the Ohm's law and these metals behave in an ohmic manner. And so resistivity, so resistance, resistivity, conductance and conductivity, these will also be part of the calculations. But we all know that we resistance and resistivity and conductivity and conductance, they're still, they have an impact on the electrolytic cells, and there are electronic modifications done to an electrolytic circuit to make it more efficient. But we can always do these calculations in physics. We don't really need to shove them in an electrolytic cell. However, what we do need to do is to be familiar with calculations such as Q equals IT. Q equals number of moles of electrons times the Faraday constant. Mass deposited mass. So mass deposited equals I times T over Faraday's constant times, I could have just written it as one, whole over, but so atomic mass of the metal involved and the oxidation number of the metal. I'm just using the word metal because most of the times it's about copper, silver, sodium, potassium and stuff. Now for gases, it'll be ITOF times 12 over 2, I think. 12, or the oxidation number, I think. The oxidation number. And we also have to remember Avogadro's So the number of particles would be mole time Avogadro's number. So number of particles will be moles times Avogadro's number. So 1, 2, 3, 4, 5. These 5 equations will form part of advanced electrochemistry. The first question. Now, you also have to remember that these pertain to so these only pertain to electrovalence, ionic, because it's the ionic compounds, electrovalent compounds that are dictated by Coulombic attraction repulsion laws that follow the Ampere, that assist in the Ampere's law when in solution or molten form. They are the ones that exhibit dipole. Well, I mean, they're the ones that undergo electrostatic forces of attraction and repulsion, and they're the ones that become ionic, and they have the thermal or electrical conductivity properties, and that's why they are able to undergo electrolysis. And obviously, in electrolysis, the biggest key player is redox, oxidation reduction, based on the principle of oil rig. Oxidation is loss, reduction is gain, and reductant-oxidant relationship, as I described in the previous videos. So now we'll move on to the first calculation. The first calculation would be now we've got a circuit. We have a circuit, so a direct current of 10 milliamps. It's best to simplify it before you're about to play them in an equation. So a current of 0.01 amps flows for 4 hours. That's 4 times 60 times 60, so hours. That's minutes per hour. That's seconds per minute. So hour cancels, minute cancels, and we're left with 3600, 3672, 72. That would be 72 times 36. 10, yeah, 14. 4. Yeah, 14,400 seconds. Now, it says that a direct current of 0.01 amps goes through 3 cells. So one cell contains silver nitrate, and we all know when silver nitrate ionizes in aqueous solution, a dynamic equilibrium is set up, and it becomes aqueous, liquid, solid. So that's what it becomes. And then the second cell this current is going through is copper sulfate. I mean, please do remember, it's cheaper to acquiesce acquiesce than melt. So melting is far more expensive. That's why. And the third cell is gold 3 nitrate. That's quite improbable. I mean, it would require you to react gold, solid gold. I think this needs to be melted. So, yeah, this one needs to be melted. Hang on. So, sorry about that. So this one, because of its high temperature and everything, it can't come in solution form. I think, yeah, very hard. So, that would be. This would require gold to react with hot concentrated nitric acid for it to mildly form this element. Now, you have to remember the question says it's one circuit supporting 3 cells. So the same so the same one circuit is supporting 3 cells, and these 3 cells obviously will so because it's now in a series circuit, the current would stay constant and the voltage would break, and in a parallel circuit the voltage would the current would split and the voltage would remain constant. So first of all, what we need to find out, first of all, just to let you know, we'll be using this equation. Now, this would be the same for every equation. This part, this would be the same. But this and this would change every single time. So what we'll have to do is to find this one out first, so we can use this and just keep multiplying it with the atomic mass of silver, copper, and gold, and then so just to let you know, the valency, the Z for silver would be +1. The Z for copper would be +2. I'm just putting +2 for your convenience so you don't get confused. And then the Z for gold would be 3, as they just mentioned. It specified it. All of these are cations, so obviously. Now, I'm working through this question as though I'm in an exam. So if I were in an exam, this is what I do first. 1, 2, followed by these 3 equations, because this question looks like it's a 10-mark question. So I'd like to impress the examiner with as much knowledge I've got, because up until till post 16, you have to display as much knowledge. It's only in university when you're asked to be specific in your critical reviews and praise the questions to what the examiner asked for. And if you write something extra unwanted, you won't get any marks for it. It's just a waste of time. So I would do this first, followed by this, and then write these 3 equations. and then say one circuit is supporting 3 cells. So that these cells have to be in series, and in series. So yeah, hang on. So because these are in series, the current would stay constant. It wouldn't split. It's the voltage that'll be breaking every single time, because one circuit has to provide it to 3 cells, and so it's the voltage that's coming under pressure, not the current. So the IT would be, I'd quickly jump over to 0.01 times 14,400 seconds. That'll be 144 coulombs, and then I would do this, and that'll be I'd quickly do this here so the examiner knows I've got the figures sorted. Coulomb, just make sure you put that little hash so that it's coulomb, it's not just looks like a half zero. So always put the units, because it's the units that'll cancel. So 144 divided by 1.1 millimoles. Millimole. Yes, that's millimole. Yeah. The coulomb cancels. Alright guys, so now I'm going to do for silver, mass deposited AG. That's how you write in an exam. So that'll be a whole over 1.5 millimole times 108 grams per mole divided by 1 oxidation. I have to mention 1, even though it's 1, I have to mention it. I have to keep it consistent because I put the Z here. If I don't put the 1 at the bottom, the examiner will deem it insufficient, and I'll be deemed irresponsible. So 1.5 times 108. There we go. So that'll be 0.16 grams. So mole cancelled, and we're left with grams. So that's that. For copper, mass deposited copper, it would be 1.5 millimole times 64 divided by 2. That'll be 1.5 millimole times 32 . Grams. I mean, I'm not using 63.5. We're supposed to use 63.5 at A levels, but just for simplicity, I'm sorry about that. And then mass deposited for gold would be I don't know what the 197, I think. Yeah, 197, because gold is denser than silver. Divided by 3. What did I do? Yeah, I should have mentioned grams per mole. Grams per mole. Oh jeez, good lord. Hang on. 197 divided by 3 times 1.5 exponent minus 3. That's 0.0985. That's 5 sig fig. I just round it off. Oh no, I can't round it off, sorry. So that's 0.085. So that's the question. So the answer, so conclusion, I would do in the exam, I would like conclusion. gold deposited, silver deposited, silver mass deposited, equals 0.161 gram plus minus uncertainty for physics graduates. I think I would give 0.005 because of equipment failure or systematic errors. And copper would be 0.048 grams plus minus. Now, how much is uncertainty wise? How much is that? It should be 5%. So 0.05. You should mention 8. Yeah, 8. It should have been 8. Sorry, it should have been 8 for a minimum 5%. And from that'll be 9. And then gold. So yeah, I'm mentioning uncertainty for statistical reasons, and you don't have to. You can just put this. That's about it. Certain uncertainty in these electrochemical cells is around about 5%. So that'll be. That's the end of the question, and I hope you'll get a whole other 10 marks. So the next question I'd like to talk about and take is a metal of relative atomic mass 27 grams per mole is deposited by electrolysis if 0.176 grams of the metal has been deposited on the cathode when the current was 0.515 amps, and it circulated for 3.5 hours. A minute cancel, and then we're left with I'm not going to use the standard notation here because it'll confuse a lot of basic students. Just get a sec, it's fine. So, and then what's the charge? And see, now it's asking you for the charge. If I were you, I'd use this equation. Mass deposited equals IT over F times AR over Z. I've got these two and this and this and this. So what I need to do is rearrange the equation for the Z. So it should be 3 because I know the aluminium's metal from my own knowledge, but I can't say that. I have to show the working, otherwise you can't get the marks. So this will be I just pop in one step because at A levels you can't just you know that after this you can just give your answer straight. You don't have to just then multiply then put the top part here and the bottom part at the bottom, and then you can skip those 2 steps and just put the answer here. That'll be 0.15 times 12,600 times 27 whole divided by 96500 times 0.176. That should give you 3. That'll be 3.005, and I would do this approximation sign and say 3 plus 3. I'd put this just to let the examiner know that I know what I'm talking about. And the answer is correct. I don't need to check it because it's aluminium. The next question I'd like to take you through is a current of a current of 1 amp is flowing for 1 hour and 50 minutes, which is 110 minutes, and it deposits copper 2.15 grams of it from copper 2 sulfate aqueous solution, and it's asking us to calculate the charge on copper. So using this equation, sorry, my marker, hang on, bear with me. It would be, sorry, all the markers are, so we've got this and this, and copper, we know the 62, so we can easily find that out. So what we need to do is to rearrange the equation for Z again. That'll be IT AR F times F dot product MD, and that'll be 1 amps times 110 minutes times 60 seconds per minute. So minute cancels. Oh, I shouldn't have. Times 64 grams per mole. Sorry, I didn't have the space, so I just put 64 grams per mole here. It's not an exponent, it's not a power, it's just that I didn't have the space. And then 96,500 coulombs per mole times the mass deposited was 2.515 grams. This marker is crap. Ugh, right, get lost. Stupid. Bad markers ruin your concentration, so that'll be 1 amperes times 110 minutes. Sorry, I'm doing this step again for the audience. I apologize. I should have times 64 grams per mole. The whole divided by 96 times 2.15 grams. So it would be that's a crazy wild, that can't be 22. So I've got this and this, I've got this and I've got this, and I just need to find this out because, so if I, geez, right, was it 2.1 grams? Yeah, that was 2.15 grams. Yeah, that was 2.15 grams. Okay, so hang on. So 1 ampere, is it 1 ampere? Yeah, 1 ampere times 110 minutes, 60 seconds per minute, times 64 grams per mole. We all know it's copper, so we obviously divide by 96,500 times 2.15. Yes, got the correct answer. 2.0359. That would be approximated to 2 plus 2. So that's correct. The oxidation number. There we go. I'll write this sentence on just to satisfy the examiner. So the next question I'd like you to take you through is pertaining to an aqueous solution. So state the names and calculate the volumes of gases formed at the cathode and anode at STP. STP is where the gas volume, 1 mole of gas has 22.4 dm cubed. So 1 mole has 1 mole of a gas, any gas, has 22 point. Sorry, that's not a point. I apologize, that's not a point. Oops. So 22.4 moles per dm cubed per mole. So one gas has 1 mole of gas has 22.4 decimeter cubed of volume expression. The current in this case is 0.025 amps. Time is 4 hours, which is 4 hours times 3600 sec per hour. That'll be 14,400 sec. So the solution, the aqueous solution is H2SO4 and the gases that will come out are sorry SO4. So sulfate ions, got that. OH ions, got that. Plus 3 H ions. So 2 H, yeah, 3, yeah, there we go, 2. So the gases that can come out, gases to be, will be hydrogen at cathode. Write the way I'm writing. This is the way you will have to write in the exam. Hydrogen at cathode, oxygen at anode. Right, so now what we have to do is to do this. So we'll use this formula, the one I showed you earlier, this one. So I'm glad it's being used. These are two formulae that I've summarized by my own experience over years. So these are the formulae I came up with after observation of the numericals. So I'll be using ITOF times compensate. So that will be So now I'll start the calculation. Sorry, I'm writing a bit small. Times, oh boy, it's not going to come through. So hydrogen's oxidation number is 1 and oxygen is 2 minus, so I'll have to put the 2 minus. So 1 plus, so, and then the next one would be now I'll write down the answers in blue. So my answer for hydrogen is 44.7 dm cubed. Sorry, 0.0447. That'll be multiplied by a 1,000. It'll be 44.7 dm cubes. For let me just write that down. 44.7 dm is cm cubed. There we go, nice little 3. And then for oxygen, it'll be so that'll be 22.38. The reason my answers are a bit off because the answer for oxygen is 41.7. Mine is 44.7. The answer for so for hydrogen it was 41.7 cm cubed. Mine was 44.7 cm cubed. For oxygen it was 20.9 cm cubed, and my answer is 22.38. So it's off by a few 2-3 cm cubed. Reason being, the reason is that this formula is, I think it's good for, yeah, that's good for room temperature. It's not, because 24, half of 24 is 12, so half of 22.4 would be 2. It would be 11.2. So if I multiplied it by 11.2, now let me try and do this with 11 instead of 12. Let me do it by 11.2 and see what we get. I think I should be able to, and I think I'm on the verge of another breakthrough in electrochemistry. Yes, got it. 41.7, that is correct. Times dm, so dm cubed times 1000 would be cm cubed. Yes, 41.7. So the next formula I'd like to write down is, now this one is for RTP. It's not for SPT, for STP, sorry, STP. So this one is for RTP and if you were to do it for STP, it would be 11.4 dm cubed. Sorry, not just no units, just 11.4. Now if I do the same here, it'll be yeah, that is correct, 20.9. So in order to convert it to cm cubed, I'm multiplying it by thousands, 20.9. Yes, so I need to write this down. So that's for room temperature, and for STP it would be breakthrough indeed, made my life a lot easier. So that'll be that. Now the next question we'll be moving over to is so the next question we'll be moving over to is calculate the mass of copper deposited. Calculate the mass of copper deposited when the oxidation number is +2 because it's copper 2 sulfate. When copper from cathode from an aqueous solution of copper 2 sulfate is how much copper from copper 2 sulfate solution is deposited onto a cathode if the same current passed for the same amount at the same time liberated 0.9 grams of silver from an aqueous solution of silver nitrate. So this is where equivalence comes into power. So we need to look at the formula again. I'm not I'm not overtly obsessed with this formula, but this formula does have its perks. Yeah, so we'll have to do some form of equivalence. So the mass of the copper needs to be used. Z we'll need to use. AR we'll need to use. We'll have to use this, but that'll get cancelled out nonetheless. The current will get cancelled out nonetheless. So what we'll need to use is equals constant. So we'll have to use this, and for that it'll be mass deposited. Sorry, bear with me. Z copper divided by AR copper, mass deposited of silver, Z silver, oxidation number of silver, so oxidation number of silver, and atomic mass of silver. So that'll be 0.9 grams times 1 divided by 108 grams per mole. This will be an unknown figure times 2 divided by 64 grams per mole. We'll have to take these two here, and then find the mass deposited. So it'll be 0.9 grams times 1 times 64 grams per mole divided by 108 grams per mole times 2 equals the answer would be 0.27. So for 0.9 grams of silver deposited when the current and the Faraday's constant and the current and the time is the same, 0.27 grams of copper will be deposited. So that's how things are for now. The next question I'd like to take you through is a current of 100 milliamps is passed for 1 hour. That's 3600 seconds. And the concentration of the 18NO3 was 1 moles per dm cubed. So silver's concentration would be 1 moles per dm cubed, and in 1 decimeter it would be, the molality would be 108 grams per dm cubed. So that's that. We've established this, and first we need to find out at this rate how much silver was deposited. So we'll have to do mass deposited equals Q over F times AR over Z. So that'll be 100 milliamps times 3600 divided by 96,500 coulombs per mole divided by 100 milli, so divided by 1,000 times 108 grams per mole divided by 1, so 1,000, so that'll be cancelling. That should be grams. Now this is the value you get with 100 milliamps, 1 hour, and this much molality. Now if the concentration remains the same but the current is doubled, so what would happen? So the current, because mass deposited is proportional to current, and current is a function of time, and is charge. Mass deposited is directly proportional to charge, which is a function of current and time. If the current goes up, this will go up, and that will go up as well. So I'll just show it to you. So that'll be Sorry, the answer should have been, hang on. So for this one, it should have been 0.4 grams, 0.4 grams approximately, because it's 36 times 108 divided by 9650. So that'll be that. Now if it's 0.4 grams, if the answer is 0.4029 grams, then when you double the current, it'll be 2 times it will be doubled as well. Therefore, mass deposit is doubled as well. Now that's doubled. Now when you now if you don't double the current and you double the time, then it would be will still be doubled. Because mass deposited is directly proportional to charge, which is a function of current and time. So the next question, so now if you double the concentration, you keep the time, the current the same, but you double the concentration. So that would be 2 moles, so that'll be 206, so that'll be 216 grams per dm cubed. So for every dm cubed, you'll have 216 grams of silver in there, in 2 molar Ag nitrate solution. Why? Let me tell you why. So 216 grams. This is how much you'd have silver floating around in 1 dm cubed. So when we do Q, that is I would be 100 milliamps times 3600 seconds, 1000, so 100 milliamps times time divided by Faraday's constant times the AR would be, so this is what would happen. 36 2 and 6. Sorry, that was a mistake. It should have been 9650. So yeah, it would double. So mass deposited is directly proportional to AR as well. So that's why it would double as well. There. If the AR doubles and mass deposited will double, so it's affected by mass. Mass deposited is affected by the current, time, and AR, and inversely by the oxidation number. And lastly, a little bit about resistance. That's voltage over current, and resistivity is resistance, a product of resistance and area whole divided by time. So sorry, whole divided by length. What am I saying? And then conductance is 1 over resistivity, so that'll be length over resistance times area. And conductivity, so conductance, yeah, that's so there's conductance and conductivity. So yeah, this is conductivity, and then you've got something called conductance. That's a different thing. I'm not going to go into solubility product at the moment, but I'm just going to do a few more questions before the video shuts down. So I think that's pretty much it. The video will shut down in about 1 minute and 25 seconds. So I hope you understood how I took you from here to here. So the philosophy of electrolysis is very simple. It is fascinating yet very simple. So I then also told you that it'll be these formulae are the ones that will help you find out your answers very, very quickly. And this will be for volume of gases at room temperature, and if you wanted to find out the volume of a gas released at an anode or a cathode at STP, it would be 11.4 divided by Z. So it'll be an 11.4 instead of a 12. So we did all those questions. I hope you enjoyed it, and I hope you understood the difference between electric potential, redox, oil rig, and all of these 5-6 formulae, and the philosophy of electrolysis in its entirety, because that's what my aim was, and I wanted you to understand that it's very important for you to grasp the principles of electrochemical calculation and analysis.